Let's hope this works. Okay. So I'm going to give it a go. Hi everyone. I will try to solve this problem that we have here, but using a more analytical approach. So basically, I'll show you how to write down the equations for this problem. All right. So the first thing I need to do is obviously to redraft this free body diagram on a sheet of paper. And the other thing I'd like to highlight is that we have here the reactions determined, which I would believe you would know how to do it yourselves. So here we go. So I will place this sheet of paper here, and I will try now to basically resketch this this free body diagram. So I have my beam. It's never too much to do it again. It's good practice, actually. This is the beam, and the loads I have applied to it, I have an external force here, which I know the value, and it's 30 kilonewton. I have an external couple applied here, which is 40 kilonewton meter. And then I have the reactions, one at E, which is 16 kilonewton, and I have another one at A, which is 14 kilonewton. Obviously, if you look at the supports we have, which are basically like this, I have here pinch support, and here I have a free support. What it means is that here I only have a vertical reaction, and here I would have a horizontal reaction as well. However, I could sketch here the horizontal reaction here, RAX, okay, and this would be RAY, and this would be REY, okay. This is the couple, and this is the force, okay. So I could do it like that. All right, have all these forces. RAX is obviously equal to 0, because if I do the sum of the forces in the x direction, it's the only one that exists. So to determine the reactions, what I do is determine reactions. What I do is to use Newton's first law, equilibrium, sum of the forces in the x direction equals to 0, sum of the forces in the y direction equals to 0, sum of the moments about any point equals to 0. So the points I have here are point A, this is point E, point B over here, and point D over here. There is no point C on this diagram. That's not a problem at all. The other thing I have are the distances. So I could sketch here some distances like this. So this is 4 meter, 3 meter, and 3 meter again. And I have sketched my free body diagram. Okay, it's really important. It's never too much to insist that we should be sketching free body diagrams like this. All right. So to determine the reactions, I would do it by using these equations. But I would presume you would know how to do it. We have the values there, so we can move on. Now, to determine the shear and bending moment diagrams, so what we do is we start by sectioning this. So I'll start by doing this from left to right always. So I will always go from left to right. I think it's easier from left to right. Okay. I need to think about the sign convention. So if you look into this sheet I've given to you, and if I look to this table here, the sagging is the positive bending moment, and the hogging is the negative bending moment, and the shear, as we see here, is negative. The positive one points down when it's represented on the right, and points up when it is represented on the left. So if you think about hands doing this motion, you can see this positive shear is like this. So one of the hands goes in this direction, the other one goes in the other direction. That's the positive shear. Okay? To have shear, you have to have two surfaces moving in relation to one another. So that's what I need to make sure. So what I need to make sure is that I keep this in mind. So the sign convention, so I go from left to right, and sign convention is like this. So this is my sign convention. So positive shear when it is on the left is up, when it is on the right is down. The bending moment when it is on the left is clockwise, when it is on the right is anti-clockwise. This is the sign convention, okay, for plus. Okay, so I go from left to right, and then I go with this sign convention. Then the other thing I do is, okay, I'll go and section the beam into one section from A to B, another one from A to D, and another one from A to D. So it's going to be in 3 steps. So let's do it. So let's start here from A to B. So what I have is the beam, starts here, then it goes, and suddenly I kind of break it, and this beam goes like that, okay? And that's point B over there. I have left it out, and this is point A. Now, my free body diagram will be like this. I have here the vertical reaction RAY, okay, which is equal to 14 kilonewton, and now I have here the bending shear, the shear force, apologies about that, pointing down, positive sign convention, and the bending moment being in the anti-clockwise direction because it's on the right, okay, as you can see there, positive sign convention. And now I proceed as always. So what I do is the sum of the forces in the I direction equals to 0, sum of the moments about A equals to 0. The other important thing to mention is that from A to B it's 4 meters, but I've cut down, sectioned the beam somewhere, so this distance here I'm going to call it X. Alright? Okay, it's any distance between X, this X is any distance between 0 and 4 meters. So basically what I could put here is that X greater or equal than 0 and smaller than 4 meter. Alright, does it make sense? So it's anywhere between those two values. So when I write the equations, I have Y direction, I have RAY minus V equals to 0. And now when I do the sum of the moments about I have minus Vx because it's negative. So if I pinpoint A and move this down, this tends to rotate in the clockwise direction, so it's negative, plus the moment, so this torque is in the anti-clockwise direction, is positive, plus M equals to 0. Okay, so that's what I have. So this is equivalent to saying that V is equal to 14 kilonewton and M is equal to 14x kilonewton meter. Okay, so this is my result for the shear force and the bending moment between 0 and 4 meter. Okay, right. Now let us continue. We'll look into these equations in a second, shortly. And what I'll do now is add here a line, and I'll continue writing here. So now what I do is from A to D. So in this case, it's 0, smaller or equal than X, and smaller and equal than smaller than 7 meter. Okay, so from A to D. All right, so what I do is again free body diagram, same thing. I do free body diagram almost up to D. So D is going to be over there, B is going to be over here, and A is going to be over there. So another free body diagram I sketch. I have here RAY equals to 14 kilonewton. All right, I have here the force equals to 30 kilonewton. The couple is outside, and now again use the positive sign convention. Shear force points down when it is on the right, and the bending moment is anti-clockwise when it is on the right, positive sign convention. And this is my free body diagram. Okay, so the shear force and the bending moment are representing the effects from the rest of the beam which I left outside. I now need also to add some distances. What I know is that this distance here from A to B is 4 meters, but the distance from here up to where I have sectioned my beam is X. All right. Now, actually, I made here a mistake. Sorry about this. This is not between 0 and 7 meters. This is between 4 and 7 meters. Okay. It's obviously it's between here and here. So it's the rest of the section. So I'm going to turn from left to right, and this is going to be valid between 4 and 7 meters because I already determined between 0 and 4. So I don't need to worry about what's going on happening before that. Again, from this free body diagram, I write the equations. which are sum of the forces in the y direction equal to 0, sum of the moments about A equal to 0. As you see, it's always the same thing. Always the same thing to determine the reactions and to determine the shear force and the bending moment. Always the same thing. So again, I will say this is equivalent to forces in y direction. I have RAY, positive because it goes up. F goes down, so it's negative, minus F. V goes down, so I need to represent with a minus signal, although this is what we call the positive sign convention for the shear diagram. But it's down, so it's minus, and this is going to be equal to 0 because I don't have any more forces in the vertical direction. Now, if I go to the moments, I have RAY doesn't do any moments about A. F does a moment which is distance 4 times F, so I have 4 times F. And by the way, it's negative because this, if I pinpoint point A and I pull down here, it rotates in the clockwise direction, so it's negative. And this bending moment is going to be positive because it is anti-clockwise, so plus M equals to 0. Okay, so I continue and I'll solve this system of equations. And on the equation at the bottom, and this is, sorry, I forgot here something. I need to add obviously the transverse shear or the shear force, which is going to be minus XV equals to 0. Apologies about that. Right, so this is my equation. So now here what I have at the top is RAY is 14 minus 30 minus V equals to 0. Okay, and at the bottom what I have is minus 4 times 30 plus M minus XV equals to 0, equivalent to, now what I have here is V equals to, so V goes to the other side, is minus, V is minus, negative, is minus 16 kilonewton, okay, and here at the bottom, if I replace there the V by 16, what I have is M equals to, so this equals to 16 minus 16, because this is minus 16, minus with minus gives plus, and goes to the other side is minus 16 x plus 120. So this is basically math going from one line to the other, and this is my result for x between 4 and 7 meters. Oh, there we go again. Right. Next step, exactly the same thing. Now I go from A to E. So I have basically 7 greater or equal than x greater or equal than 10 meter, because the whole length of this beam is 10 meter. Now I have the full body diagram. You will use the full body diagram almost. So basically if I sketch it again, it's like this, but I don't really reach E. So that's E's over there. And what I have here, I have point A, I have point B, I have point D. Okay, so what I have is, I have here RAY, I have here the force F, I have here the couple D, M, sorry, at D. Okay, and then I have here again this transverse shear, and I have here the bending moment. Now, in order not to use the same letters, what I'll do is, instead of calling this M, I'm going to call this T, and I'm going to call this T for torque, okay, just for the sake of being a little bit clearer, because I'm using M for bending moment, so I can now sketch M here. Again, this is the positive sign convention, V going down and M being anti-clockwise when it is on the right side. Okay, so what I do again, I write the equations. Same as usual, simply write the equations. So what I have is basically, so maybe I will use another sheet of paper now. I'll just try to keep this visible, say they're at the top, all right, and I'm going to remove this from here, and let's see if I can keep this visible. Right, so I'm going to basically write the equation. So what I have is sum of the forces in the y direction equals to 0, sum of the forces of the moments about A equals to 0. Always the same stuff, which is equivalent to say that what I have is RAY, so this one, minus F, which is this one. T doesn't appear in the sum of forces, it's a moment or a couple, so it's not here in this row, so I continue, this is not there, minus V equals to 0. Okay. Now on the row underneath, what I have is RAY, moment about A, is 0. F, moment about A, I forgot to add here some distances. This is 4 meter. This is 7 meter. And this is X as usual. So it's my variable. It's anything between D and E. Okay? That's where I am now. Right. So, sum of the moments about A, what I have is F is negative about A minus 4 times F. The torque is negative as well because it is rotating in the clockwise direction, so it's minus T. Okay, and the V is negative as well, minus XV plus M equals to 0. Equations start growing up. Now I'll start replacing stuff on the equation. So RAY is 14, F is 30, minus V equals to 0. Okay, and at the bottom I have minus 4 times 30 minus T is 40 kilonewton meter because it's given. I'm going to show you here again. 40 kilonewton meter. All right, and I have also represented that in my original free body diagram over there, 40 kilonewton meter. So I can now basically write minus 40. Okay, that's it, because it's a torque or a moment. I don't need to multiply it by any distance. All right, so this distance 7 meters is not relevant because the torques, couples, moments are free vectors. I have that in one slide. You can see that in my, I think it was on the second session, week 17, I believe. Anyway, minus XV as usual plus M equals to 0. So what is yields is, and I'm going to be a little bit slower than before, V equals to, again, minus 16 kilonewton. And on the row underneath we have minus 120, minus 40, minus X times minus 16 plus M equals to 0, which is equivalent to, I don't need to write down the first row, it's minus 120 minus 40 is minus 160, okay, plus 16x, okay, plus M equals to 0. So the final result is V equals minus 16 kilonewton and M equals minus 16x plus 160, and that's it. That's my final result. And this is my equation between x greater or equal than 7, smaller or equal than 10 meter. Right, and I finished. So, I finished and I've obtained, basically, if you look into this carefully, I've obtained basically, oh, this is probably not the best color to use, but 1, 2, and 3 equations over here. All right? So these 3 equations on 3 intervals will determine my diagrams. Now, let's look into them. I'm going to write them down on a separate sheet of paper, okay, so that it's easier for us to do it. So I'll have you, right. So I'll do that, separate sheet of paper. I think it's going to be easier. And following what we have, what we can see is that from 0 to 4, V is equal to 14 kilonewton, okay, and from 4 to 7, oh, I have to probably do, and from 4 to 7, so I don't need to do that actually. From 4 to 7 and from 7 to 10, it's the same thing, it's minus 16. So V, I'm going to write it down here. I can write it as V equals to 14 for 0 smaller than equal than x smaller than 4 meter, and minus 16 kilonewton for 4 greater than x greater than 10 meter. And the other thing I have is the bending moment, m is equal to, now m is 3 rows, 14x in kilonewton meter for x smaller equal than 0, smaller than 4 meter. It's going to be minus 16x plus 120 kilonewton meter. Is it correct, 120? Right, minus 4 times 30, okay. 4 minus x, so more than 7 meters. Sorry, I'm taking a little bit long. 16x plus 160 kilonewton meter between x more equal than 7 more than 10 meter. Okay, I've written the formulas, all the formulas here. Okay, right, so I have the shear force here and bending moment here, and as you can see I have split them into different intervals, ranges. Okay, so let's plot them then. So I'm going to do a big plot. Okay, big axis here, and now I'm going to do one horizontal axis here and another one, say, over here. I'm going to call this x. Okay, this is going to be in meter and this is going to be in meter. Okay, now I have many important points. I have the point at 4 meter. Okay, I have the point at 7 meter, and I have the point at, so that's 7, 10 meter, and that's where my beam finishes. Okay, here I'll plot the shear force in kilonewton, and here on this diagram I'll plot the bending moment in kilonewton meter. Okay, so let's start plotting. I'm going to start with transverse shear, or the shear force. Shear force is 14 between 0 and 4. It's a constant. So I could say here this is 14. Okay, well, I'm going to use blue here probably. This is 14. I will always use the same color here. I don't need to use colors. So 14 from 0 to 4. So it's always positive and like this. And then from 4 to 10 is negative and it's minus 16. So it's going to be like this. So this is my shear force diagram. If I want to emphasize it, sometimes we represent like this, saying this is positive, saying this is negative, and we add these lines. It's very typical to represent it in kind of a shaded area, okay, so that it is easier to understand. So this is my shear force. Now I'm going to plot my the bending moment. All right, the bending moment is going to be a little bit different. So from 0 to 4 it's 14x, right? 14 times 0 is 0, so that 14 is 0, that's 0. Okay, and that 14 times 4 is 28, 56. So I'm going to say that's 56 over there. Okay, the other thing I noticed that this is a linear relationship, so I can say it's positive slope, it's 0 here, so that's a linear relationship like that. This is between 0 and 4. Now from 4 to 7 what I can see is the following. Maybe I need to use a calculator to help me, right? So let's see. Here is this calculator. Now minus 16 times 4 plus 120 is precisely 56. So this is correct. It starts here. Okay. Now I'll do the same thing. Minus 16 times 7 plus 120 is 8. So at 7, so that's what I have written there, 7. At 7 we have 8 over there. So this is 8 here. Okay, and this is linear relationship, as you can see. So it goes down like that with a slope which is minus 16. Basically the slope, as you can see, is the same as the shear force. I don't know if you've noticed that, but that's an important thing. Sometimes can be useful. The slope is the same as the shear force. Right. Now I go to the other range, minus 16x plus 160. And I'll do the same thing. Minus 16 times 7, because that's at the lower side of the range, plus 160. And I obtain 48. All right, 48. So at 7, this equation gives me 48. So when I have the couple, and if I call this 48, suddenly the bending moment jumps to 48 kilonewton meters. So it's going to be jumping upwards like that. Next, what I have is minus 16 times 10 meter, the other end of the range, plus 160, which is 0. So at 10 meters, it's 0. So my bending moment diagram is going to be like that. So I have the equations representing them. Now, it's always positive, so I could just say here plus sign, and again shade it, which is really common to do when we represent this type of diagrams. You'll see that in textbooks and everywhere, shaded areas to better illustrate the diagrams. Now, let us see if this is correct. So I have done this in MDSolids before, and I have done this before as well in class, and what you can see is that these are precisely, let's see, I think we can see them, precisely the same results that we've obtained. Okay, this is from MDSolids, and this is from our analysis today. And you can see that the results are the same, and that's how we get the final equations over here. You could get them as well in MDSolids by going up here, I think to the options, I believe. It's quite easy to pick them up. Okay, right, I hope this is useful. Thank you very much for watching.